Welcome. I've been doing embedded software in one way or another for more than 30 years. Most of that's around safety and security. And real-time operating systems has been my specialty. So you're going to get that tack on this topic today. And my hope is that as you go through this, that you do ask questions. If you have a question, you want to ask a question, you can wait to the end, but you're feel free to go ahead and interrupt. I'd rather get your questions answered than just talk. And with that, I wanted to share, when you're looking at systems that are doing machine learning or AI algorithms, this is one that we trained, I guess is 6 years ago, 7 years ago at this point, but it tells the story about how you can take an image, and this is actually using, I don't have all the sensors on this image right now, but it had LiDAR, radar, and 2 stereo cameras pointing downstream. And you can see how it's detecting the lines. The dot up there is where it's saying, I want you to shift your steering a little bit. We don't have it steering right now, we're just collecting the data. But now I'm playing it back through that algorithm. And so you're seeing a machine learning algorithm. One of the questions is how much compute do you need to do these types of algorithms? So we'll get into that a little bit. All right.
Maybe you already answered this, but where is QNX being used in that? In which car or which thing is that being used?
I can tell you some cars, not all cars. We're in 255 million vehicles worldwide today. And so the Ford F-150 Lightning was in our booth at CES last year, so that one I can mention. The Jeep Wrangler, does that sound right? Grand Cherokee. So that one, we have software running in there. I know Karma, which is one of the EV manufacturers, they're running our stuff. We're in 19 of the 20 EV manufacturers. One holdout. Pretty much, but I can't say that.
Well, you didn't. He did.
Exactly. It's usually at CES. We'll do a big announcement, and I think there's 3 vehicles in our booth this year. So if you check in at CES and look at our posts, you'll probably see what cars we have there. We don't have a relationship to tell everybody all the cars that we're in. But a lot of them, we're in different parts of the vehicle. We're in the infotainment system.
Yeah.
So we'll run QNX for safety in front of the driver. And then the infotainment system will hypervise Android and then run that as a guest. We have customers that are running multiple guests for the back seats as well. If you want to entertain your kids as you travel across the country, it's important. And we're also, so that's the infotainment side and the cluster. Autonomous drive, which is what I showed you before. So we're doing that as well. And that's the different levels. And I have a slide on that. Also audio. So you think about the next generation vehicle, lowering that noise floor so that it sounds better. So you could have a medium grade vehicle and a high-end vehicle, and the high-end vehicle has it tuned so that you don't hear the noise from the road.
So
minimize it.
Super Cruise and Blue Cruise, or can you not say?
I can't say.
Okay. I would.
And actually, I don't know them all.
Okay, but that's the 2 big ones.
Yeah.
Why QNX over some other OS?
Wind River. Wind River was an example of another real-time operating system.
Yeah, no, I get that, but I just.
So I'm sorry, the question is why QNX over?
It's wrong. I'm just saying why QNX over something else. Why is that taking over so many cars?
That's a good question. I mean, certainly we have the safety and the security, and we built into the industry early on. So we had early wins in the infotainment system because we had the safety. They looked at us for other pieces, and we just picked up the market. Wind River, late to market.
Yeah.
And so you already have 900-pound gorilla QNX in the market, and Wind River just hasn't been able to compete, even though they were bought by Aptiv. Is that right?
Well, we were also owned by Armin.
Yeah. Well, Wind
time, so that helped.
Well, Wind River is also the 3,000-pound lead weight that does that.
I should tell you, I didn't give you that part of my intro. I used to be the product line manager of VxWorks at VxWorks 653 over at Wind River. So I know that product extremely well, but I like some of the things we get with QNX. And one of the pieces I'm not going to talk about today is our tools. We're both using Eclipse-based tools. And periodically, and this goes to other companies that I've worked at, we would see failures in the debugger and you have to restart. When you restart, starting your application over again. I just don't see it with QNX. It's a really well-oiled machine in terms of interacting with the debugger. So, all right.
I like QNX. It wasn't my comment on it.
No, that's okay. And you're talking about my old product. So I have one of these. It's like, oh yeah, but that's my old. Anyway, it's all good.
You need a 4F-150 carry software.
I'm trying to buy one. I actually just was mentioning to my colleagues, like, while I'm out here, I think they're less expensive here than they are in California. So maybe I should buy one tomorrow morning and drive it home. It's a long drive. All right, so what is the Internet of Things? We're going to go through that a little bit. Look at the interconnected things, some examples. Safety and security. Really the key aspects of why you would use a system like this. And then we'll get into some autonomy and artificial examples, artificial intelligence. Look at the interconnected systems, data flow management, so processing data on the edge, as well as moving data to the cloud, and then cloud management, data aggregation, and then the system lifecycle. Now, the Internet of Things. You can define it different ways, and I've heard many different definitions of this word, but this one, devices with sensors and actuators that process data locally and are connected to other things. So if you're a standalone machine, let's say you're a defibrillator, you don't connect to the internet, you're not an Internet of Things. You have to have some, it could be wireless, it could be a different protocol, but if you're not interconnected, then that breaks it. And then there's different applications. We talked about automobiles, and we'll talk a little bit more about how that works. Phones, I think phones is one of the biggest. When we were driving here today, the first thing I did is I dropped in the address in my phone, and we're looking at the traffic. And we're relying on that traffic information. Well, what is that? That's everybody else's phone that got stuck in traffic, uploading their data to the cloud. And then we see, oh, is it better to take this freeway or that freeway? There's a big accident. Let's go ahead and take a detour. So I look at that as a prime example and a good use case. Robots, patient monitors, and then even these thermostats and weather stations. If you think about when you go somewhere, a lot of times you'll just go to the cloud and say, weather.com, what's the weather in Austin? We're going to get that weather report here. But if you know where you're going, there's other sites that you can pinpoint a sensor. And it's got a bunch of sensors. You can see how the weather's developing there, but get local weather that matters to you. So I would say, and the difference between them is the weather station gives you that data, it's raining, and then the thermostat can say, oh, I want to change the temperature at home. I actually have a sprinkler system that's on the internet, and I can configure it to listen to the weather station. So if it's raining, don't bother watering my lawn.
Which brand do you have?
It's an open source one that I built called Open Sprinkler.
Okay.
I didn't want to pay anybody, and I'd rather build a system. So you build it by yourself. It's based on a Raspberry Pi.
I'm gonna watch it.
I used to have, I forget the brand, but it was not internet connected. And I'm like, I got to go to this next step. It broke about 6 months ago. Let's go ahead and go to this one. Cool. All right, now I'm going to go way back, an example from the 1900s. This is a jet engine, and jet engines have some problems if they end up with vibrations in them. You've got engine monitors, so there's engine controllers. They're monitoring the health of that engine. And it used to be that you would sense that something's going on. You may alert the pilot if it's critical, but that record when they land would be processed and, let's put the plane in maintenance. What if we could shorten the downtime? And so what you do is you go ahead and have those sensors on the machine, but you're going to broadcast that or send it up to the cloud. That comes down, and they say, well, I'm on a transatlantic flight from San Francisco to Tokyo, and I've detected that there's a failure in the engine. Still flying, but I've got an excess vibration. And I've seen this before. So the machine learning that's been done in the cloud can say, oh, you know what, we've seen this before. It's probably this part. Turns out that part's not in Tokyo, but it's in Seoul. So I'm still flying over the Pacific. They can actually ship that part so that it lands in Tokyo before I land in Tokyo. Now they have a maintenance crew. That plane is down much shorter period of time. They're not waiting for a part. They're able to do just-in-time delivery. Yes?
Is that a use case to leave, or is that an existing story?
It's from the 1900s.
I know, but,
In other words, this existed before we had the term Internet of Things.
okay, now the fact that we had sensors.
Yes,
Malaysia
yes, this
flight.
was running on airframes in the 1990s, probably
There
the
was a
80s.
Malaysia flight they couldn't find. They were looking at the data. They were still transmitting data.
Oh, from some of these other, oh, you're right, yeah, from one of the engine
Transmitting data
controllers.
For the engine, they got back to Boeing and Hogan Airbus. And
Yeah.
They knew the plane, when the plane stopped communicating, therefore when it
Impact.
impacted.
So this was tied to the airlines, supply chains.
The supply chain, exactly. So it's part of you call it the advanced systems for how do we minimize downtime, increase profits on each airframe. So that's the goal of it. But it's great if you can do it while the flight's in process and go ahead and schedule it. You order the wrong part, it's still down. It's there. Yes.
I've got a friend who's 777 pilot. He tells me that the computer signal to the destination that there's a maintenance issue, but then it decides to pilots need to know about it.
Yes. And wouldn't you want to know if you're the pilot?
Well, you would think so, but you know what? If you don't need to disturb the pilot, why would
If it's not critical,
Yeah.
I had a flight from Ottawa, Canada. We were flying to the UK.
Yeah.
And we got over Newfoundland. And they said, well, an idiot light turned on the dashboard, so they won't allow us to proceed over the Atlantic. So we can either land in Newfoundland, which if we can't fix it, there's no spare parts. We're stuck. We can go back to Ottawa, same case. So they actually took us further back to Toronto. And instead of landing at 8 in the morning, we landed at 2 in the afternoon after they put us on a new airplane. But yeah, there's rules about that, how they put them together. Another one is surgical robots. In the situation in the slide, you can actually see that we're running, the surgeon is looking in his view of what's going on with the patient, has some haptic feedback controllers, and then the patient is behind him. You're in the room. Now, this is still an Internet of Things because we're also taking data records from this surgery and we're uploading them to the cloud. Yes.
Yeah, Anderson done used to doing surgery with robotic arms these days.
Mhm.
And we had the company I work for, we did a project for a surgical instrumentation company out of Michigan as well. So this is very prevalent now in the healthcare industry.
Mhm.
Was this in Da Vinci?
I can't confirm or deny, but I've heard the name. But one of the other things is, and now let's extend this. So you have a surgeon that's a specialist, and now I have, let's say they're a soldier, and they're in the Middle East somewhere, and they have a condition. The specialist is in Chicago. If they had this machine, they had doctors over there that could set it up and get it running. You could actually do the surgery remote. And now there's a little bit of a delay, so you want to minimize that. That's where time-sensitive networking comes in. Deterministic communications so that we can get as close to real-time feedback as possible.
You need to talk about what network that runs over. Is that satellite or is that undersea fiber optic?
Oh, the network here, you can run it on any backbone. So it doesn't have, I mean, obviously if you have one that you can have low latency on. So we know that it's running in an undersea cable, get a little bit faster than going through satellite. So it depends on what's available. And we'll talk about ways to do failover if a system goes down. All right, now into the safety and security piece. Definition between safety and security. On the left-hand side, we've got the seatbelt. On the right-hand side, the key. And then you boil it down to the first sentence here, that the safety systems are protecting people from the system. And that could be the occupant of a vehicle. That could be somebody that's walking nearby or riding their bike or another vehicle. It could be the guy that's doing the maintenance. Your goal as a designer is to minimize the impact on people from the system and failures that might occur. That's opposite from the security, because now we're going to be protecting the system from people.
I like that.
These are the definitions that you go to Webster's, you can pick up those definitions. But I like how those two set up. Yes, is there a question back there?
I was just scratching.
Ah, it's a head scratcher. There we go. But if you look at these two use cases where we look at safety and we look at security, there's really no safety without security, and there's no security without safety. So they kind of go hand in hand, even though there's different specs. Does that make sense? All right. If it doesn't, I'm sticking with it. Okay. Functional safety, we're going to go a little bit into safety and then into security. When you look at the functional safety standards, you see a bunch of them listed here. And really want to focus on two. And this is the automotive, ISO 26262. It's a derivative of 61508. But then we have aerospace, the DO 178. And when you look at those two standards, they really are doing different things. Think about the 737 MAX. If you remember the problems that they had a few years ago, one of the design goals of that airframe when they started out was, hey, let's not have to retrain pilots. How do we do that? Well, the airframe is larger. The capacity is larger. The weight is larger. The distribution of weight. So let's put a control system on board that we put in fighter jets, MCAS. And you can look at the studies online if you're interested. It's fascinating to see what happened. But that MCAS system was made the airplane fly as if it was the earlier generation 737. It's beautiful when things work, right? Because now they don't have to retrain the pilots. They saved a lot of money and get awards at Boeing for doing all these wonderful things. Until you realize that the way that you do DO 178C is you specify what you want to happen. So you take your high-level requirements, break them down to low-level requirements, break them down into either your test cases, your test plan, your actual test cases, the results, and then over here would be your actual code that you write. And it's so descriptive that I could click on any line of code and say, this line of code belongs to this low-level feature. I should not be able to click on any piece of code that isn't to a requirement. What that says is, the way they designed that airplane, it did exactly what they intended it to do. What they didn't do was follow some of the stuff in ISO 26262. In 26262, it actually looks at the systems themselves. Now let's compare two different systems. Let's compare the airbags. Now airbags, you would all say that that's a safety feature, but how often do we have airbags deploy? So how many people in here have had their airbags deploy in a vehicle? It's about the same ratio as we did before.
Yeah.
Yeah,
So
actually, yeah, trying, guys.
So you're not driving next time I go.
And I guess I'm not either, because I did that as well. And I had them deploy. But you look at how many different people, how many hundreds of thousands of hours we've cumulatively driven, and there's only been 2 instances, and those were point cases. So when you need them, you want them, but the amount of time that you rely on that system is very small. Now, compare that to anti-lock brakes. If you've got a modern car that's got an anti-lock braking system, you're using that every time you get in the car. So ISO 26262 says we need to test that anti-lock braking system a lot more. And it asks the what ifs. What if this fails? We need to make a change. What didn't happen with this, with the 737 MAX, they didn't say the what ifs. They had a single point of failure. The pitot tube failed and it thought it was in a stall. MCAS system says, you know what, in a stall, I know what to do, nose down. And so the pilots were continually fighting. They would take it off controls, but MCAS was still underneath. So their design goal was specifically to remove training when that's the exact failure. They needed to train on the what if. And that's why. So I actually contend, and I'm going to be speaking at a FACE webinar next week, that holding to this standard versus this standard, that this one makes a lot of sense. And that this one, in some ways, you get overconfidence in the way that they do their testing. So I'd actually like to see a blending of them, or actually look at ISO 26262. And we're coming to a head because we have vertical takeoff and lift. In California, we're starting to have taxis. So if you want to bypass the traffic, you can fly from San Jose to San Francisco, which would take you 2 hours on a Friday afternoon, and you're there in 20 minutes. So it's coming. I don't know if you have one in your driveway, but we need to solve this problem. Okay, safety. When you look at safety, freedom from interference. And this first column, spatial, that's space, how much memory we've allocated. When I allocate memory for a process, I care that that process is interfered with. I don't want anybody else getting in there and mucking about with that code or that data space. So need to make sure things are walled off, which means for systems to have MMUs. You have a complex system, it shouldn't be run on a system without an MMU. Temporal or time, we want to make sure that if you have a set of tasks that are running, maybe they launch when they see a certain event, and all of a sudden they see 400 events in 1 second. So they start launching all these tasks, they start doing all this, burning up all the time, and then you have no time for your critical tasks. So ensuring that you design your system in a way so that there's enough time for your system to be able to do its job. Message passing, this one, there's really 2 methods that you can use. You can use just standard message passing in the way we do it. You're going to set up a copy. It's not 0 copy, there is a copy. Why? Because this spatial, we don't own that other memory. So if you can tolerate it, you use message passing, and it's a little bit inefficient in the system, but you gain safety. Well, we need it because we're processing high performance compute. We got lots of data coming in. Okay, in that case, what you do is you run a shared memory window between the different procedures or processes that need to run. And you can get around it, but that needs to be in your safety case.
This is one of
Yes,
the
sir.
arguments, well, some of this is one of the arguments why a lot of governmental code is being rewritten in Rust as opposed to C.
Yes, Rust is one of those up and coming languages. We don't have, I haven't seen hard requirements, but I have seen some customers asking, we have Rust support in our new generation.
All because of this.
Yeah, and it changes the way that you write your code
A lot.
to make safety a priority rather than afterthought. Because C, you can shoot yourself in the foot, which is why I like C. It's a great language.
Yeah.
And then communications. How do we get data between different devices that are either local on your system of systems or the remote? Do we know that that datagram got through? Can we detect a failure? And then react accordingly. If a sensor goes down or the server I'm talking to goes down. On the security, this starts down here. It kind of goes around in this circle, but it starts with a root of trust, actually provisioning keys and hardware. That would be the most secure. We have a device manufacturer that wanted to make sure that when he went to his semiconductor manufacturer, when they go make chips, they say, I want 200 of them, that the people making the chips don't say, well, let's make 400. And then they could sell them as aftermarket. Or worse, they could change it and go to a substandard piece, and now it's put out on the market. And what do buyers do? Buyers and companies, they're going, well, how can I get this at a lower price? hey, here's Joe's Engineering over here. They have the same part and it's 40% less. Let's go buy it. And now all of a sudden you have substandard parts. If there's any failures, your brand gets dinged on it. So you want to make sure that you're doing that. Securing the supply chain, that would be not just what you're building, but now I'm building some, or I'm taking some parts from other suppliers. Make sure that that's secure. And then look at all the components from a software perspective. What's running on the target? Secure communications. Make sure that you're using authentication on the machine and authorization that you have access to the data. So that's kind of it. I'm not going to go through all the details here.
Hey, Chris. Yes,
It's Steve, but yes, please.
Oh, I'm sorry.
That's
And
okay.
that's the first time I've been.
Chris is my evil twin.
All right, well, say hi to him too. Have you ever heard of the Captain Crunch whistle?
Captain Crunch. Oh, yes, I did.
Well, when you're talking about securing the comm channels, it's what came to mind is how people could just be, out of band.
Yes.
signaling. And it was, anyway, it's really funny. So yeah, that's a great point.
Yeah, yeah. It's funny how some of these things, ways you can get into systems. One of the early cracks in automotive was somebody coming in through the infotainment system with an MP3, but the file wasn't an MP3, and yet it was read into the system. And somehow they launched it, and they were able to execute code on the infotainment system. Couldn't do a lot from there, but if you have a connection to the CAN bus, and the CAN controls things, you can actually issue commands.
Can you move your backpack?
Oh, I'm so sorry.
No, Bob.
You're better. I'm a face for radio, so.
No,
This is another way of kind of looking at the same thing from, we call this the onion slide, but it's looking at the different levels of being able to secure your target. And you don't have to deploy all of them, but as we were saying, the trusted hardware, the ECU or engine control unit, authentication, so making sure in the manufacturing. One piece I want to touch on is the security policies. What we do is we allow you to turn on the security poly manager and run a battery of tests. How are you going to use it when it's out there in the field deployed? So it captures all the states. So this application reaches out to that application. Okay, we capture it as a state. If you find something that you need to do that's not in that list, it will trap. And the example is you have a motor controller, and that motor controller software is controlling several motors and those motor device drivers. Device drivers those are interconnected, and that was captured, so that's legal. But the motor controller may have reached out to the internet or to phone home or do anything, but the device drivers did not. And lo and behold, another software release comes out, and the system would trap because we flipped it around and said that's all you can do is what we provision. So we capture the states, then you flip it around and say that's all we let you do. Lo and behold, the device driver reaches out to the internet. It was some engineer just trying to collect stats on his driver, figure out what's going on, and it trapped. That code shouldn't have escaped the lab. You can make the choice as a system designer. Is that a good thing? Probably not. Let's say no, but maybe for development, allow it. So you can set up different security policies. So there's some other pieces here, including the temporal and spatial, that come in to affect security. All right, autonomy and artificial intelligence.
So I've got a question, Steve.
Sure.
All this overseeing software is on a BlackBerry platform. What's like?
I'm sorry. So all this stuff is on a BlackBerry platform, but
No, is it on a BlackBerry platform?
QNX.
yes.
I don't think it's
So two things. You're going to hear my talk as not directly involved with QNX, but this slide comes right out of our deck. These are features of QNX. There's a few things that are not. These down here they're part of QNX, but are part of BlackBerry, but not QNX specific. In other words, you can buy them as an add-on. And then this one here, the runtime integrity, is a third party.
Okay.
But everything else that has blue underneath is a feature of the operating system.
Okay, so I just want to make sure I understand that I'm a little confused. what's the connection? I thought the QNX I know is a real-time operating system. So what's the connection when you have BlackBerry and QNX put together side by side?
Oh, here?
Yeah.
Okay, so the question, why are these side by side?
Yeah.
And the answer is that you can think of QNX as a subsidiary of BlackBerry.
That's
And I'll give you a little bit of news that stay tuned. By CES, you'll probably see a little bit more about the QNX branding.
okay.
But right now, just think of it as a wholly owned subsidiary of BlackBerry.
So really, okay, so all the stuff that we're seeing here at the end of the day is BlackBerry.
Yes, except when I showed that video at the beginning and when I get into machine learning, you're going to see some features that I'm just talking about the industry, not specifically about QNX.
Okay,
But
well,
this is, so our
let
safety
me get
features,
down to transaction level. If I were to buy this stuff, who am I going to transact with? QNX
With
or
Rich.
BlackBerry?
QNX.
That's what I want to know.
Unix is a product, BlackBerry is a company.
Okay.
Unix is also a product by QNX,
Okay.
which was a company until BlackBerry bought them, sort of subsidiary.
Okay, that's what I want to understand, that piece, what that.
After BlackBerry.
I was not be following BlackBerry for a long time.
Yeah.
Okay, got it. Okay, thank you.
Make it a little more complicated. RIM bought QNX. and
The RIM,
BlackBerry bought
it was RIM that was on BlackBerry.
Yeah.
So it makes it a little more complicated, but you get a little more of it. It's
So end of the day, that, so if you're going to transact all these features, right,
Mhm,
I buy it, right?
Mhm.
But so the logo that you're going to sell it is QNX.
yeah.
the real-time operating system
We are
is
a wholly owned
QNX.
subsidiary of BlackBerry.
Okay, so you're talking about the operating.
Yes, yes, except for where it doesn't have blue. And I'll put, because you're asking a detailed question, adaptive partitioning is in QNX 7. We've gone to a different structure in QNX 8.
I like that, very interesting adaptive partition.
You're familiar with the feature, or?
I know partition.
Yeah, this is time partitioning in the system. So we're going to do it different ways with SDP 8, the next generation.
Just a quick question on
Sure.
that trusted hardware piece. Do you have specific targets? And like, are you looking at ARM targets? Or are you looking at?
The good question. So
Yeah.
is it in terms of the trusted hardware? Are we
Yeah.
looking at specific ones? And I would say that certain ones have already been done, but usually it's customer focused, customer specific. So if they have an ASIC, then we're going to do it with them specifically for their hardware. But you can look at other ones that have TPMs, trusted programming modes in there. So trust zone, but hardware underneath that can do key storage and whatnot.
Okay.
Then that will be specific to, say, a Xilinx or an NXP.
So do you run on ARM?
Yes, we run on ARM, and that'll be coming up on the slide. So ARM and Intel are the two main
Any
technologies.
risk five involved?
We get the question about RISC-V. It's we've related from Rich and I, from our perspective. We've gotten that question. We brought it up to product management. Product management is tracking it. They don't see enough traction. Once you get a big manufacturer, say an NXP, says we're going to build RISC-V, that's probably when we're going to go ahead and implement it.
So they're x86 and ARM targets at the moment. When you
Yes.
Compile. That's what I was trying to.
Yes, x86 and ARM and Cortex-A.
Oh, okay.
Yeah, not the other cores.
Okay.
Okay. Now, going into artificial intelligence, I remember going to a conference and looking at neural networks in the 90s. And so, or maybe it was even 80s. It was early on, some things going on there. But you can see how these circles get larger, looking at deep learning going on, machine learning, and then artificial intelligence. And I really look at the difference here. When I'm doing machine learning, I'm adapting, I'm training, I'm figuring out what's going on. And then when I deploy that, I'm doing it as artificial intelligence. And you can see how we can do learnings based on a subject that you have.
So explain that, because I'm a huge believer there's no such thing as AI. Doesn't exist.
Okay.
Not in the near future. That we're still in machine learning. That I don't see, when I think about test cases of things that we've developed. See how we learn by pump failure or something fails, we can detect that and make decisions, learn from that and couple that to devices. But what I don't see is, I've never seen an application where the device says, you know what? I need to start like this automotive. I need to look at stop signs. Heck, I might need to look at traffic lights. Oh, those lines on the street, that's probably a good thing to look at. Man decided that. Some man or woman decided that we need to look at lines, lights, and then what's red and green? I don't know that I know what that means.
It's all sophisticated pattern.
Yeah, so it's pattern matching, but it goes back to, it's a human that I haven't yet seen a computer that says, huh, doing this work better, I need to look at the color of the clouds because that's going to make my driving different.
Right.
Without a human saying, rainfall's bad, pay attention.
Yeah. Yes.
I'm with you on this. And that adding to what you're saying, is the problem that I'm seeing right now with all of the react that they're talking about and what it's not mean because I had AI class way back on time. Is the fact that the contextual aspects of images or the decision-making process currently is not there. So, I'm not going to get. So, do you have that in what you're calling in your system of AI?
The answer is, this is where we're getting away from our product and into our customer's product. So a lot of our customers are doing autonomous drive, full autonomous drive. They're building these algorithms.
Okay.
And things like NVIDIA Drive is based on QNX. And so they're using that GPU to do high performance compute to recognize what's around them, the road signs. Now, I believe they were trained to say, here are the road signs. So they didn't just come out of the blue and say, I need to look at signs, but here's all the signs that you might need to watch out for.
Problem that is there, you went to the autonomous. That's what Tesla has had problems is that it's either rock on a hillside in Colorado, it's not going to know what the hell is going to hit it.
Yes, well, they don't run QNX, so I think that's one of their first mistakes.
That we know of.
That we, who knows?
That's what I want to understand, because what you're saying is right, that to make it AI, you got to have a decision engine there that's context based as well. And right now, when I see what they call AI today, it's purely a rules.
Yeah, it's pretty impressive what they can do. I actually took.
It is.
It's impressive. Don't get me wrong.
It is.
Well, I got in the back seat of a car that nobody was driving, and it took me to the train station during rush hour, and it was showing me on the display all the things it was recognizing, and it was like, oh, here's a pedestrian. I'm going to mark them in red. Here's another car. Here's the car behind the truck. There's a truck right here, and it could see there was a car moving around the backside, and I was impressed with that. I thought they did a great job.
Even for us humans, is the lighting at dusk and dawn.
Yes.
And I had an accident with an 18-wheeler because I thought that the trailer was an open road with no traffic, and they decided to change the lane. And I didn't look far enough to my right to see that it was getting right at.
Yeah,
That's a
you are
problem.
correct.
Yeah, that's a problem that is not being solved. Even with
Well, they do have certain things. Your sensor set can help in that environment. So it's going to degrade if there's a lot of light pollution, but you can use different parts of the spectrum. And if you just do the narrow visual band, but you can also look at the infrared, so you're getting heat.
Radar,
LiDAR, all of them.
Yeah.
So you took, and then the sensor fusion really matters because I'm bringing it all together. So I don't think the problem's fully solved. We were promised autonomous drive would be here today.
Well, he did the visual only. Camera only.
Yeah, which is an interesting spin. You know, can you do it with camera only? And with a camera that can get a lot of visibility across a huge spectrum, including infrared.
But you're talking hyperspectral cameras, right?
Yeah.
And so far, you can still break them with a ray of sunlight.
Yes. Yes, I don't have the slide that Rich had in his presentation, but he talked about a painted kid on the road.
Oh, that's right.
Yeah.
And the painted kid on the road, if you look at that, oh my gosh, if I'm only looking at my cameras, that's a kid. I'm going to hit my brakes and going to go around, and yet it's a painted image on the road to look like a kid.
Looks like nothing with LiDAR, it looks like nothing with infrared. But it looks like a little girl playing with them all.
Yeah, if just sitting in the car, you yourself would be startled.
But that happened, every once in a while.
Yeah, no, it was a real test case. It was, somebody tried to pull the cars, painted a picture of a little girl that rode. And when Tesla had one of their early accidents, they hadn't turned on all of their sensors.
The LiDAR,
Which was one of the problems, and the other one, the truck had gone perpendicular to the road. And when you try to solve an engineering problem, oftentimes you want to reduce the noise, reduce the other things. Well, they were filtering out anything that was across the road because it was a sign, but they weren't measuring how high the sign was to the road.
Mhm.
So when the truck was sideways, it looked like a sign. So no, that's nothing. We can walk. We can drive
Decapitated.
and decapitate it.
Yeah.
Yeah, it's something you lose your head.
Yeah. You'll get a question in the back.
We did sign the video.
They talk about autonomous aircraft.
Mhm.
What they found out is the flying public wants somebody in the airplane to have skin in the game.
Yes.
And so.
Yep.
It may be sweet, but they want somebody there
Yeah.
to invest it.
It was interesting when they had that pilot that got the co-pilot out of the cockpit and he locked the door and then he crashed it into the Alps.
Yeah.
And I thought that's
Yeah,
one
yeah.
case where I think that if you have command codes and it's like, okay, I know there's a hijacking, I'm going to use my top secret command code to take over that plane and just tell it, go to the nearest airport safely and land. And then you take care of that.
Yeah, that's kind of where they're going with it, is that I'm a private pilot. They even want me to be able to have a button on the airplane where if I start feeling incapacitated or my wife
Uh-huh.
sees she can push the go button.
And it'll drive you safe or fly you safely
Yeah.
to the nearest airport.
Yeah.
That would
Wow.
be good.
The autonomous cars are more safe than human drivers, even today.
I'm totally
But
believe that.
there's still problems. It's not.
There's still problems, but you look at how many accidents we have because we're looking at our phone or somebody's arguing with their wife and boom, nobody ever has arguments with their wife.
it's a question of trust.
Well, I think the biggest problem with autonomous vehicles today,
Sure.
to really summarize this, if we could start from scratch and build an autonomous vehicle, they have a great life because it all talks to each other, the B2B stuff, B2I, all that, it all works together. But the problem is we have to, and we will forever have to have the 1940s vehicle on the road or 1980s or whatever that's there. We have to pay attention to something that is not part of us. And so you can't have, because the natural way, like onboarding cars from the highway coming on board, that could be made so easy if all the cars talk together.
If they were
If
cooperative.
they were cooperative, but
Yeah.
you're always going to have that 1940s car,
Well,
1980s.
California, we're good at legislating everything. I've told my kids that you're getting your driver's license, and they all did, but your kids will be prevented from getting a driver's license.
Prevented.
The
Yeah.
problem is,
Prevented.
in
I think that's what will be
California, as
legislated.
crazy as California is, they let other drivers drive in that state. I mean, you could drive across the border. It
Oh, that's
falls
true.
into the ocean. We still get to drive there, which means.
Well, I don't know. We could make that illegal too. I don't know. It's future, but there's one that just happened, that's happening right now, is that if you buy a huge motorhome, California's made them illegal to purchase in the state next year. So that's in
Really?
2 months.
But you can drive it in the state, probably.
You just can't buy one.
It's like in California, you have a California vehicle, you have American vehicles you buy today, and you have California vehicles you buy today. You take America's vehicle and drive to California and register.
I don't know if who knows?
You may be able to register.
We're a
You
good
live there.
red tape state, so I don't know.
You still live there, maybe it's your second home, and whatever,
Uh-huh.
or it's your, something, but we're so.
You're assuming you'll have gas
Place where
stations.
a
We might get rid of those too.
We're never at a place where a state or the country says you can't drive a red Barachetta, or song, but to ride the 1940s, 1950s, 1960s, 1980s car, Mustang, a classic car,
Yes.
1900 car.
I told my son, He should buy land near San Francisco Bay that's just got a bunch of hot rods. So when they make it illegal, you have a private land, private track, and a bunch of hot rods. Yes.
That quote's very, very interesting and it's very deep.
This one here, FDA defined
Yeah,
machine
I was
learning.
thinking, why would the FDA do that? Then you read the whole thing, realize.
Yeah, techniques used to design and train software algorithms to learn from and act on data when intended to treat, diagnose, cure, mitigate, or prevent disease.
Yeah, it applies to high tech as well.
It does, and actually, one a positive in this new landscape of machine learning, they set it to look at different cancers in the brain, and then they gave it so the data set. Here's a bunch of cancers to look for. Why don't you characterize them? And now we're going to hand you a set of data, and just tell us what you see. And it went. We've identified all 6 kinds. Here's 2 more that you didn't know about. And then you have a doctor look at it and go, you know what? These are cancers. So it actually did help in that case. Yes.
One of the problems with the autonomous vehicle issue that Intel is working hard about is insurance liability involved.
It is. It's a huge problem.
A whole different can of worms by itself.
Who's going to take responsibility for that? Somebody else's talk today, it was, who's going to take responsibility for open source software being consumed in devices? Because it's open source, it's out there. I write it, I put it out there. Am me, the author, being nice and putting my code out there, am I now liable? So it's a big issue.
That is open source.
Yeah.
It could, very well.
There's a few other issues that are also ending open source similar to this
Yeah.
already.
I think we're a litigious community.
We are good at that.
And it's gonna be a problem for all this stuff. Yeah.
Yeah.
I call it fun.
All right. No, I think my next slide, I see if I had my screen, I could see, but it might be talking about, no, it's not. It's coming up soon. But the different types of autonomous drive, anything from driver assist. I know you're in a slow zone. I'm going to go ahead and give you that. Platooning, we talk about cooperative. So we could set a set of cars that are going to go from Dallas to Austin. You just get in that platoon and you fly it, whatever, 120. Or the full, and I used to say it, distracted driving. That would actually be just somebody
That's a
going to work.
right?
Yeah.
So
She's reading a better thing than we would read.
yeah. Well,
It's just
somebody said it was sexist that I had that picture. I'm like, it's just a person. Anyway.
I think going back to your previous topic, I think you're gonna have zones on freeways like you have
The high occupancy.
That's where the trucks are gonna run and the trucks are gonna be autonomous. So you will not be able to ride both of them at the same
Well,
time.
if you're driving on I-35, Dallas to all the way down, right, east of Texas, the NAFTA trucks are only allowed in the right lane, so that all 35 is 693 for the feet, and they're only allowed in the right lane, so that's the 10 to
We said it was way up 45, but that's the problem with 45. The 18-wheelers want to pass another 18-wheeler, but they don't want to go 70, 2 miles an hour. They want to go just 71, and they barely find pass. When they need to go 80, like the rest of us, zoom to the cross.
Yeah.
Oh.
I think you had a question over here.
Oh, I was just gonna make the observation, I mean, I know it's in the literature, but Lexus has a deal in the vehicles that are starting with the FY, the 25 models, where you get on a highway and it's like cruise control, but if traffic slows down, your vehicle slows down.
Yeah,
Yes,
I've experienced
automatic.
that on a Corolla.
Oh, mine does that.
5 years ago, they haven't doing it a long time back, and it took me all coming back from San Antonio to figure out, man, they put some of this advanced stuff into the Corolla.
Yeah,
So these are options,
okay.
the idea
Yes,
is
they are.
it's just that, to them, it's
It's-
just the next step past cruise control.
Yeah, it's
GM and Ford have it.
stuff up here, not that. Yeah.
My Honda Palisade does everything but full autonomous. I mean, I don't know what level it's technically at, but it'll go to a complete stop on the highway. If I want to change lanes, I hit the lane change, I hit the take fuel, and it goes over. If it can't, it beeps and waits till it can, and then it moves over.
Yeah, that's probably level
The other
3 or
one is
4.
interesting. Even if you are not changing lane, as you hit the lane divider line, it will pull you back.
Oh, yeah, that, they got that. I mean, they just, all that stuff's built in my Honda was okay, but Hyundai, it will freaking go around the high five, it'll do curves. If there's a remote line, country roads won't do well, but there's a line, center
A
line,
clear line, a center
a clear
line, and line
And there's a
divisions.
new exit, one exit wrong. So some old systems, you're driving down the road, there's an exit, it follows the exit, the line that goes to the exit. No.
Yeah.
It says, oh, there's a center line, there's a line over here, and I see that one varying off, but that's,
I'll just stay with the
I'll
center
stay
line.
with this one over here.
No, that's good. All right, when you look at, and this is QNX, the gray area is where some of the autonomous features are. So bringing in the different cameras, LiDARs and radars, you can bring them into different sensor engine control units, ECUs. And our sensor framework will take that, it'll make them look like it's similar. So all LiDARs will kind of look the same, all radars will kind of look the same. Then when it gets brought up into the main vehicle computer, you do the sensor fusion algorithms on that. And of course, so in the perception, you want sensor fusion, the dynamic model, what's static and dynamic around the vehicle, where can I do my path planning, and then eventually it goes out to action. That's usually a different core doing the actual control of the vehicle. And so all these gray boxes are things that are not part of
So you're
QNX.
already handling autonomous driving. What else do you do?
Besides autonomous drive in the vehicle, or
Just for application.
Robotic surgery.
yeah, so robotic surgeries, we're in infusion pumps, we're in industrial robots. Anywhere where you need to have, I would say one of 3 things. You need safety, you need security, you need robust or deterministic behavior. When those things come together as key for your device that you're building, that's when you look at QNX or road
So you
operating
have
system.
this, you've got it tied back to IoT. That means those devices you're in, they have a SIM card.
No, they don't have to have a SIM card because we can be talking through an onboard Ethernet. And matter of fact, this whole system could exist on the system without connecting to the internet.
So
But I could on the back end, and I have a slide I'll talk about that in a minute.
so what's going on today is that they're using the LiDAR and radar information and they're comparing them to updated LiDAR and radar maps in the cloud and then making decisions. What's going on today. So there's a back end side. Yes, today. Yeah, mine does this exactly. So for instance, my autonomous does not work if it can't pull me a live radar or LiDAR map to compare to the data.
Mhm.
It will disallow.
Maybe in automotive, we're also in construction equipment, mining equipment.
Yeah.
And a lot of other things with that.
Well, you can have full autonomous, but what's going on now is that a lot of stuff is doing LiDAR maps to compare, right?
Mhm.
Just
And
because
we'll do
the
some of the
endpoint
algorithms
comparison.
you can put in here are doing SLAM. So you basically create a map. And if you're underground, you're in a mine, you don't have access to GPS. So you're creating that, and those will be your locations you'll go back to. Of course, in a mine, you're tearing down the walls as you're
Yeah, but
expanding.
they're definitely comparing cloud LiDAR maps to data and updating.
There is an interaction.
Yes.
And part of the problem is construction. So
That is the
personally
biggest.
hate, lane assist. Because I'll go into construction zone and the lines aren't quite perfect and
Mhm.
we're trying to do that. And I never apparently use that little thing on the side of the turn signal. I never do this, but as a turn signal, I just kind of.
So what happens is when they compare the data to
Most
see,
use the turn signal. You know, it's because of lane assist that I use the turn signal. Before that, I never did. But because I don't want
It's
that
trained
thing doing
you.
this to me.
Yes, it
I
bites
use
you.
the turn signal. So it's actually helping me drive.
So it doesn't take control, you know, manually override.
You can override.
Yeah.
You just have to turn.
Yeah, you
mine automatically turns off the automotive when it sees a mismatch. So if it does see construction or reroute or
Yeah.
detour and it doesn't match, it turns the automation off.
Which car do you have?
Because I have a GM.
What?
I have a GM.
General Motors.
General Motors, I check.
But also the other side of that is when we said that those perceive and decide are
Correct.
not done by us.
Correct. Yeah.
The Fords and GMs and all those
Yeah.
others who may or may not use our software, they want to do their own perception and decide.
Well, they're pulling in.
We give them the structure
Correct.
to implement.
The
We don't
safe
want
environment,
to do
secure
that kind of
environment.
stuff. We want to give people the structure to do it themselves.
But it is comparing your data to.
Absolutely.
Yes.
Sometimes, depends on the
Yeah,
application.
depends on-
So I see some other sensor acquisition, pre-processing.
Uh-huh.
That's a pretty high CPU intensive.
It is. Well, it can be. We actually work with a partner that does something with, and I didn't talk about it here, 4D LiDAR, where you're getting,
Wow, 4D, is it?
it's FMCW, frequency modulated continuous wave LiDAR, that gives you in a single scan, it can say, here's a point in space and here's its velocity vector. So you know your velocity vector as you're driving. Maybe I'm driving straight on the highway. A ball bounces into the street. It now will track it, and it knows its velocity. So in one frame, it knows if it needs to avoid that or not.
It uses a Doppler.
And then reading across there, you have dynamic loading, redundant central controller, node fault on. What kind of computer system are you running this on?
Well, it can exist in several. So we have customers that are using those FMCW LiDARs, the 4D LiDARs, and they're running it on an Intel platform.
Okay. So
But we have a lot of customers, and if you look at NVIDIA with NVIDIA Drive, that's based on QNX. They'll only sell it on QNX. And that's where you're getting high performance compute on there. And there's a problem with it on my next slide. We have a question over.
Sure, Qualcomm as well.
Yes.
Yes.
I was at the CES, I saw the Siemens presentation. Is Qualcomm working on something, I mean, making a building its own local network, the factory, the robots could understand, that's a QNX system.
It could be. I'm not familiar with that. I know that Qualcomm is a strong partner of ours, and we're used in a lot of automotive applications.
When you say Intel platform, give me an idea. We're talking about an Atom or we're talking about a Xenon?
Xeon or Core i7, i9, i3, i5, i7, i9, anything that's got a full MMU.
So you have multiple nodes, fault tolerance.
You can do multiple nodes. You see two nodes here in the picture. There's one behind.
Yeah.
So you could actually have two competing systems that are going to do that. The other thing you can do is if, let's say I lose enough sensors out here, this system could say, I'm throwing my hands up. And so you could actually go to a limp home mode. The car's only going to drive 15 miles an hour. It's going to pull to the right lane. It's going to get off the freeway and phone a tow truck.
So you have, I'm trying to understand, is when you say redundant central control nodes for fault tolerance, that is standard? Or that is only the customer?
Well, it's the system design. So it's the system designer themselves. So a Ford would have to put it in and say, you know what, we want to have this.
Okay.
And that's part of ISO 26262 to say, I want to get to ASIL D, the highest level, but right now my hardware is only at ASIL.
And you're running down.
B or C. You can run it on Intel chips. Now you need the safety certified version. So now you might look at the hardware and choose what is the best platform.
Okay.
But you can run it on Intel. It'll physically run.
Okay.
Now, one of the problems, we talked about high performance compute that's running here. Let's say we've got some machine learning that we've done, and we said to the machine, see, I want you, we trained it on dogs. Now see dogs. You see the dogs? Maybe the image is too
Lots
small.
of dogs, yeah.
Lots of dogs. This image, it's part of Google's Deep Dream. So you can the wiki page there. It's kind of hidden, but if you look at Google's Deep Dream, you'll actually see how they characterize, and they basically overtrained the model and basically said, find dogs in this picture, and it found as much correlation as it could. So you can't overtrain these models.
So how do you guard against that?
Don't overtrain. The other thing is you train on horses, I mean, you want to train, if you're using a machine learning model, you want to give it scenarios that are likely. And showing it a horse and telling it to look for dogs is probably a bad thing. But you know, you want to also give it scenarios that it won't, that are unexpected. You want to have it be able to discern what to do. Yes.
Many years ago, I did training inside Cheyenne Mountain. I did the missile and space portion, but I sat next to guys that did the air portion.
Uh-huh.
So I always caution when you get into training like that, because they had a scenario where they had terrorists hijack a civilian aircraft, crash it in New York City, and they took it out of training because it would never happen.
Of course not.
Because at the time, nothing like that would ever happen.
That's right. This was pre-2000s, right?
Yes.
Yeah, it's a good point. So you want to train on that. There's a great study. I can't remember the name. Blue team, red team. They did some war scenarios, and they
This is the
took.
one where they were doing somersaults?
No, no.
That was.
This is one where they set up a whole scenario, like maybe it's the bad guys are in the Middle East, and so you set up the U.S. forces or coalition, and they have all the supercomputers in the world, and then they take an old crotchety old admiral that had retired and say, "You run the Middle East because we want to get kind of degraded a little bit." And the thing is he went, "Well, I know what I'm up against. I'm up against overconfidence in the sensors. So let's figure out a way to get out of that. And let's do some stupid things that they don't expect. Like put some missiles very close to the vessel and launch them just at the beginning. And it overwhelmed the systems. So they had to then back out and do it. So if you look it up, gosh, I don't remember the name of it, but it was probably 20 years ago. And he won that battle, but they had to halt the test. So let's do it again, and let's put restrictions so the good guys win, right? We have to have the good guys.
Yeah, but I'm sorry to step in again,
Yeah,
but
sure.
Famous in World War II, the Japanese they were not really computers, but they ran the Battle of Midway before they went to the Battle of Midway.
Yes.
And they had their.
I'm sorry, you're
adversaries.
saying they actually ran a simulation of the Battle of Midway, assuming where the U.S. would be.
Yes,
Would be.
and the U.S., they said, oh no, the U.S. is not going to come from the ocean, open ocean. They're going to steam out of Hawaii after we attack Midway.
Yes.
And they changed the rules of the simulation because initially they didn't win. They would lose.
Ah, interesting.
So
I
they
hadn't heard
changed
that
the
part.
rules and
Yeah.
made it so that the U.S. carriers would come out of Hawaii. And then when the U.S., because we broke their encryption,
code, which is an interesting
and
story
we
in
weren't
itself.
where
Yeah.
we were supposed to be, and in 5 minutes, the course of the war shifted radically.
Yeah, yeah, it's a fascinating story. There's a couple of movies, one that was done in the 70s and then
Yeah.
recently.
Yeah,
The one
say what
recently
way?
is-
Yeah.
I
Not
mean,
ran it Midway, yeah.
they've been done really well, but the point is the one recently is, I mean, they even got the characters to dress like the people from.
Yeah, there
Yeah.
was a documentary.
But
about-
Woody Harrelson, I'm sorry, I had a problem with Woody Harrelson.
Yeah, but he
Admiral.
tried to look as much like the Admiral as possible.
Yeah, I still see Woody.
It's hard not
Anyway,
to.
Exactly.
But, you get on different spectrums of it because, when you do training, you don't want to do negative training, i.e.
Right.
your example.
Over training.
But you also don't want to get into a part where something that is possible, you're excluding.
Yeah, Murphy is always around the corner.
I think there's a lot of research going on here, and we haven't fully cracked this nut. This is something that we've got to spend a lot more time on. And we have vehicles that are driving, so we're doing something right, but it's not everybody. 10 years, maybe. All right, moving on.
10 years, it's really going to be flying.
Well, VTOL's coming to California. Next year we'll be testing it.
It's not new, Hawker Siddeley have VTOL jets.
Oh, yes. Well, we have VTOLs that have been in production.
F-35 has some of those functions.
Yes, absolutely. The F-35 does. There's a company called Joby Aviation that flies them. They're doing research, and actually they were bought by somebody or heavy investment from Boeing.
Toyota invested, Toyota's up
Is it
past
Toyota?
800 million investment.
Yeah.
I'm sorry, I'm a Bosch employee, but I work at Toyota Motors of North America.
Ah, fantastic.
Airbus was also doing one.
And
There's
it's
a lot.
a very crowded field. The issue
Yeah.
right now is there are a lot of companies that have a lot of craft that they want to take off and landing. And some of the companies, like the German company Lilium, German federal government chose not to give them 500 or 50 million euros. So they filed the German equivalent of, we're dissolving the company unless somebody
Oh,
gives
really?
us money. The
Interesting.
Williams, but there's Archer, there's Volocopter, there's the Chinese
yeah.
Ehang. There's the Eurocopter division that is keeping theirs under tight wraps. There's, there's the Boeing version. There's a company called Beta Technologies that has some really wonderful stuff. That's
I think it's coming, but I also think the autonomous drive on the two-dimensional plane that we drive on, usually, not the plane that flies.
And initially, there, at least in my mind, what working with the FAA is the hub and spoke, like kind of like
To get into congested
like,
areas.
No, you have an DFW. Incoming will be at 1,000 feet above ground level, and they'll come in just this one vector. They'll come in and land. Outgoing will go up to 3,000 feet and go
And
out.
straight out, or
on a straight
different-
line to
different.
the place it's landing. And despite the fact that they want to have pilots for a while. There's, I mean,
Yeah,
that's a
it's
totally
interesting.
different
It's
thing.
coming. It's coming.
Yeah,
Both of them are coming.
I mean, they fly.
Yes. So compute intensive, we talked about this a little bit, but just to show that you've got the Cortex, and I say the Cortex A's, they have full MMUs or Intel cores. We're actually starting to look at some of the Cortex R's that do have enough of an MMU that will start running on some of those. But not on the M cores. Those are too low level. They don't have a full MMU. The interconnect here, so now we're doing offload. This could be NVIDIA with general purpose GPU or GPGPU. Could be an FPGA, it could be an inference engine. And then the different interconnects could be shared memory, could be PCI, with shared memory. M2, I've even seen this inference engine running across USB. So
M2 is the message.
what's that?
M2 is the messaging, right?
It's the M2 connector. It's got something like PCI that it plugs in. It's a little different spec, but
FPGA is an unusual offload choice.
well, it's not unusual when you look at the likes of AMD who bought Xilinx
Okay.
and they're going, oh my gosh, look at this juggernaut NVIDIA. How do we compete?
Oh, so
And they have some stuff that they're trying their best to bring out.
so they can reconfigure on the fly? Is that the-
Well, no, you can just run your compute intensive algorithms in an FPGA.
Yeah,
So
that's just so far behind.
it is
Yeah,
right now.
that
Their
seems-
goal is to catch up.
That's an odd.
We would love it if they did.
It's very much.
It's hard to catch up with the giant.
And NVIDIA's been doing it for 30 years, they don't understand.
Yes, they do. But
Yeah.
AMD also knows GPUs.
Sure.
So
want
I don't
NVIDIA to
know.
win.
What's that?
I want NVIDIA to win.
You want NVIDIA to win.
You got some stock.
I got stock.
There you go.
It's literally gonna be
Everything.
And the FPGA solutions are actually faster for certain algorithms, but they're far fewer than the fit. And they're not as versatile.
Yeah, it seems, yeah.
Yeah, and
Right
their
application
integer
is
processing.
perfect.
Yeah, I mean, if you're dedicated,
For an inferencing engine dedicated to a particular task, they're fine. But they don't train well. There's depends on what you're doing, like
Yeah.
everything else.
I would think the only benefit would be that you could reconfigure it for tasks, right? But yeah.
You could reconfigure it, but even with the NVIDIA drive, I don't know that they're reconfiguring it on the fly.
Okay.
That they
But part of
program
the
it
problem
with.
with AMD from a corporate standpoint is their burden with their commodity products.
Mhm.
Who wants another Ryzen processor? It's all commodity compared to Intel. That's no longer the money maker. Those are just commodities that go into things we have right there.
Mhm. All the laptops and
Yeah,
whatnot.
just, whatever.
Yeah.
A penny here, a penny there, maybe somebody makes money.
Yeah,
They make money in it. The new money is in.
The AI chips that are coming out of
other
NVIDIA.
things. Then, laptops are
Blackstone?
commodities now. Laptop is desktops, PC, that's a commodity business, and there's no money in that.
Yeah.
Relative.
I know, but when I go to buy one, they seem expensive. For home.
Especially if they have the GPU.
Yeah.
Yes, exactly.
You buy laptops for $200, it's like, it's the low end.
Yep.
Then you can spend money. If it's like a car, there's to some degree, so worse, at least cars are some money, but these things are commodities.
Yeah.
Coffee maker.
What I found is that, this is a tangent, but some of the laptops, they've gotten so consumerish that I really prefer my work laptop that can take a beating and it just keeps on going. And I bought some of my home ones. I had an HP one that would flip over and touch screen, and now things are starting to break on it.
Yeah, no, you wouldn't.
I don't want that.
I agree. I still buy my wife right now, and for Christmas is gonna be a new laptop.
Yeah.
Getting say business class because I want.
You want that
Whatever.
robust, durable platform.
Still
All right.
working on it.
So the next piece is how we do the interconnect. And this is something called the DDS, Data Distribution System. If you're familiar with ROS, the Robot Operating System, ROS 2, they standardized on DDS. And this is a publish and subscribe system. So we have a couple of nodes here. They're talking to the cloud, but they don't actually need to know the topology. This node here just says, I'm going to publish this topic. And anybody in the network, it will route saying, oh, there's a topic here. Do you want to subscribe to it? And this cloud said, yes, subscribe to it. Same thing from that node over there.
MQTT or dedicated DDS?
Yes, yes.
So
You
dedicated.
can use different ones. I detailed DDS here,
Okay.
but it's similar.
MQTT.
We used to have our own with PPS, publish, subscribe,
Yep.
but we're standardized on DDS now. And there's some commercial versions that are available through partners. There's some free versions out there as well. And the beauty of DDS is since you don't need to know the full network topology, somebody does, but you could actually sever links, and if it has another path, it'll actually reroute underneath the hood and be able to do it. So it's pretty impressive what you can do with some of the networking stuff. OpenAMP is another one. This is where we're talking between the big cores, Cortex A's with Cortex M's. So you see many cores over here, 1 to 2 cores typically over here on the little cores. And it's usually with a shared memory buffer that's shared between the two. And then it interrupts going little to big and one going big to little. And you've got it.
If cores, not separate CPU. But they're not physically.
So when I use the term CPU, I'm talking about a core. So a lot of these things, like if you're on I might have a quad max that has 4 A cores and 2 R or M cores that are available.
Separate chips, could it not?
Could be separate chips, but now I might not have the memory bridge.
Okay.
So it depends on how you interconnect it. But it's possible. It's possible to do that, and it's just a matter of how we pass things around. So I'm talking about probably a more tightly coupled system. But you can take advantage of it. We had a customer that was building drones, and they're like, we need to take advantage of I forgot it was an M or an R core. And all right, fine, because we do a lot of processing here. We don't actually run on the M cores, but we'll enable you, and we'll enable you with something like this. They brought the operating system up on the M cores, those little cores, and then they started talking to the ports, Sierra port, with a big high data rate, and it was doing some processing, some communications level above it, and it fell over. It couldn't complete the job. Well, let's try that same application over here and just move the device over here. Put a process.
So that had
You could
2
do it.
cores. And it's together on both cores?
No, it's so you could say it's a single core,
Yeah.
and I'm going to dedicate it. I could have 2 cores. Some of the R cores can be done in lockstep, so it depends on your system architecture. And does the R cost that you run down here support it? You have some choices.
This new idea of performance and efficiency. What it's
Yeah,
starting
it
to
is,
get.
but when we start looking at it, and that customer went, oh, we're not going to hit our target here.
Yeah.
Let's go ahead and run it on these cores. Application came up, there was plenty of bandwidth. So we were over that hurdle. All right, time-sensitive networking. I didn't have a good slide, except the fact that when we got into this at the beginning, when we had customers asking for time-sensitive networking, I'm like, why, yes, we can do this with a partner. And then the question comes back, wait a minute, what substandard is needed? It turns out there's a lot of capabilities with TSN under the hood. So it's all based on precision time protocol, but what are those sub-protocols that are going to run on top? So you really need to understand what you're trying to accomplish with TSN, and then make sure that your solution has it. Some are in software. Software is costly. Some are in hardware. You need to have an Ethernet controller that can do it, But once you have that, do you do the rest in an FPGA or in hardware, or do you do it in software? Anyway, knowing what spec you need to hit is important as
Are
well.
all of this in your network?
No, this is through a partner. And we learned that the hard way at home. It's definitely through a partner.
Each one?
But you need to know, yeah, actually the precision time protocol, which is based on, so that lowest level, we have a solution there. But everything above that, it would be third party.
Each of the IoT numbers.
And you can get a lot of these from the same.
Oh, okay.
Yeah. So now it's just a mix and match depending on what your solution needs.
There's a lot of hardware vendors that have a TSN solution. And then it just becomes like a PCI interface to us. So it's complicated. There's hardware solutions, there's software solutions, there's software solutions, and then it's not everybody implemented the same thing. And then one customer for one service will request something completely different to another from another service, or maybe versus orange. Because it got to be a mess.
Yeah.
What he meant is we lost a deal over this, so we kind of have a higher level.
Yeah, there's a little bit of a sore spot there because of the way that the literature was written. But we learned a lot about the spec, so we're now trained in it. And these recognizing that when they say TSN, we don't say checkbox, use this partner. We say, which protocols do you need? And then we make sure that the partner can do it. And if not, what's it going to cost?
But if you just implement 802.1, you should get all of that.
Nope. I mean, you have to do the subspecs
Oh,
based
really?
on,
Okay.
so if I want to do path control and reservation, I need to implement QCX.
Like 802.11, which has a bajillion subspecs.
Yeah. And this is probably not an exhaustive list. It's the list that our customers have, different ones have asked about. So it's a set, probably a subset.
Pretty good.
All right, cloud interactions. Now, one thing that you need to do when you're looking at the Internet of Things on the edge and doing compute, you don't want to send all that data up to the cloud. So what we do is we implement a virtual sensor. Think about a battery in an electric vehicle. This battery health, we don't want to send the voltage all the time, send the current all the time, send the heat all the time. We want to pre-process that data and send chunks of data up to the cloud. And the cloud can then aggregate that across the fleet. Say, wait a minute, why is Mr. Olsen's car, its battery is depleting more than it should? And based on that, they can say, oh, alert me to say, go get your car serviced, you're still under warranty, do it. Or it might say, look, Mr. Leadfoot, you need to slow down. You're overdriving the car, which is burning out your battery. And then I choose to drive how I drive. But you can see how pre-processing some of that data instead of sending everything up, you can minimize how much data is actually transferred and yet still allow the cloud to aggregate that data and do some work on it.
And it saves on your cloud bill.
The costs, yes, the back end costs. When you look at the life cycle of the device, we're showing a medical robot here. You want to think about how am I going to do that secure software update? And we established in the security, the root of trust, everything that runs on the system has to be signed and authenticated. But this thing comes up and says, well, let me just check the cloud, see what's going on. So it has to go out to the cloud and authenticate the cloud. Are you really who you say you are? Cloud says, yes, I am, hands back the right key, the right secret. The other side is the cloud reaches, it doesn't trust but verify, right? Now it's going to do the verify step and say, okay, are you really who we think you are? If you have the right secret, you can give a response. Yes, you are. Now we have a link that we can trust. So we encrypt that communication. And then it's just a question of what do you want to provision down here? Do we want to do just a file? Do we want to do a file system? Do a data record? Do we want to completely change out the load that's in there? So this is different steps that you can do based on your use cases. All right, we're getting near the end here. I did want to say a little bit about QNX. We've talked a little bit more about it than I normally do, but so QNX, we have the operating system, we have the hypervisor, and then we have versions for safety. So if you want to run QNX there, we have stacks. The sensor framework we talked about a little bit. There's other ones here. Here's a list of protocols, and it's open source software. It's by no means extensive. We have a lot more that's available than what's there. Partners that we work with that have different solutions. And then from a guest perspective, we can support Android, Linux, QNX, Ubuntu without much modification. I think that's mainly the pieces here. This QAVF is interesting as well, being able to easily swap out to the next generation if VirtIO is already done in the guest.
Okay.
QAVF is the answer to VirtIO underneath. So you can take Android 13, 14 is available, bring it in, and it should just bolt. So instead of weeks of development, you're done in a couple of days.
You're heavily relying on libvirt.
Yeah, a lot of VirtIO for being able to communicate it. And then when you look at communications, there's different ones. There's one that I want to bring out on this slide, and that is if you wanted to run the GPU and use it in a guest. Because some applications, NVIDIA doesn't want us to run as the operating system, even though we're their choice for an NVIDIA drive or a medical robot. They won't talk to us. They're focused on making money, and they're doing it good, great job.
So
So what you
proprietary
can do-
OS is basically what you're saying. They
What's
want
that?
Some sort of proprietary OS.
No, well, it's running QNX, but they build the board support package, and they build the interface to the GPU. So our answer there is go ahead and run Linux as a guest, run your GPU driver in Linux, and it's going to be passed through straight to the hardware. So now you can still run it. And for a while, NVIDIA would detect that it's hyperplexed and it would fail. And one of my colleagues had a customer that said, no, go ahead and investigate it. And lo and behold, it now works. So
They could break it later.
that's true. It's not a necessarily permanent solution. But
Pass-through drivers are hardware specific in many cases.
well, they are, and you need the driver. And if the driver's detecting that it's hypervised, you do. But I think NVIDIA saw that enough people were wanting to run in this configuration. There's other modes of communication. And the only other one is where you para-virtualize the device. That's where you're using VirtIO.
Okay.
And that's the standard that we've settled on.
That's what most things use.
Yeah.
We even get advanced versions of Google so that we can complete the integration. So you can migrate to the next version and it's already been checked out. We really can accelerate that.
You mean on the Android side or on
The Google Android will get an early
Okay,
version of
yeah,
it.
yeah.
There's 2 embedded versions. It's
And they have a big team that's already working with QNX. They've standardized on QNX. Because Google doesn't want to do this layer anymore. Another chip comes out, they're having to do a board support package. No more. If they use QNX and we do the board support package, they can just focus here, do the VirtIO drivers. They're done.
They don't want to deal with the hardware driver.
They don't want to deal with that anymore. Major in the majors. Yes, you had a question.
Where do you see the company going? What's the growth path?
Where do we see the company going?
You know, what's the growth path here?
Unix.
Well, I'm still gonna see the BlackBerry.
Well, because I look at them as sort of, and I'll call it BlackBerry Classic, where you're doing the stuff. They're still doing that work. They're making money there, and they'll continue to, but we don't have a lot of visibility into that side of the business. From a QNX perspective, we just built QNX 8, and it's revolutionary. I didn't have any slides in here, but it really did solve some of the problems with high performance compute on these Cortex-A cores and Intel
So
cores.
can your software, can also be usable for this basic general purpose application?
Our software, absolutely. So this stuff down here, you can put POSIX-based applications in here all day long, and we're happy. You can take libraries like ROS2 that's built for Linux, recompile it for QNX, and we're running it right here.
So any application that's running on Linux today will run on.
As long as it's using the POSIX APIs, because we're fully POSIX PSE 54. Some of the other real-time operating system vendors do 52, 53, which is not process level. We do a full process model. So we can pretty much take everything over There may be some configuration and cross compilation. That's the real hard part that needs to happen. That's it.
It's also interesting that you're doing the word package stuff because waiting for mainline DTB files to be made versus doing your own custom stuff. That's very interesting as well.
Yeah.
Because you're doing certification, I assume, when you do that with the hardware vendors. For the
It depends.
packages?
When they ask us
Okay.
what the customer needs, we won't do things just on spec. We'll do things when the customers ask us when it
Gotcha.
gets to the hardware specifics. But we do enable like the Intel FUSA parts that have some of the functional safety pieces and libraries, then those need to be ported and run on
So
QNX.
you just said something, when customers tell us what they want, I thought a customer is mostly automotive.
That is true. For QNX, most of the lion's share of the company is in automotive, but there's still a lot that are doing general embedded. So robotics, industrial controllers, mining equipment is not considered automotive. So that's one that Rich and I chase. We went to Mine Expo about very interesting, standing next to some of the machines that we build, and we meaning just humans. These huge machines that I'm pretty tall, and the bed of the bulldozer or the dump truck, I guess,
Oh, that can be really odd.
that was like 5 times my height. I was just like, really? And how many metric tons they can pull out of a mine every day is just astonishing. So you had a question in the back.
You don't have to answer if you don't want. Say like Mercedes Benz operating system.
Uh-huh.
That it actually branded.
It very well could be, but I don't know.
Anything if I do next day, you're all over the place. It seems like everybody's talking about the little operating system. Don't take it, sir. It's like-
Well, I would say that it very well could be. Yes.
How long does it take? Like you said, you're in on Cortex-A, right?
Uh-huh.
So if they come up with something new, how long does it take to import the software?
So going from ARM v8 to ARM v9 to ARM v10, as we go to those.
Yeah.
I would say that we get early access to some of that. So when we saw the new chips, the Honeycomb and what's the Graviton 2, those were running ARM v9, and we had early access to them. We run in the cloud on those today, and the Honeycomb we run on today.
We were months before we got a good portion of it, but not years.
Yeah, anytime there's a major architecture
8, 10,
shift.
8, 10 BSPs, it wasn't like we were months.
Okay.
You know, it wasn't a year because we released this in December
Of
and
last
we
year.
already had 4 or 5 or something.
Yeah, but most of those were ARM v8, not ARM
That's
v9.
true.
But we did do those other ones.
The ARM9, the 93 and 95.
And then-
You said the Honeycomb.
The Honeycomb and the Graviton, pretty new.
So
Yeah.
it was months, not years.
And we do run in the cloud. I have a slide that we'll talk about that in a minute. So
Blackwell, it could be a running part with Blackwell. Probably.
the Blackwell, good question. Who knows what they're going to put in automobiles next? But if they put it in and they support it, then obviously we'll do it. But I don't know that they're ever going to put that compute intensive platform on a vehicle. All right. In conclusion, there's some more slides after this, but in conclusion, we talked about the Internet of interconnected systems, systems of systems, the need for both safety and security, and then I mentioned it again, robust safety and security. That's important. We talked about autonomy and artificial intelligence, data flow management, how you move data around safely and securely in the system, and then cloud as well. So that's the main portion of my talk. And then I had one special that we did today.
Now, I have to ask, now, I've been recording this, but I don't know, I got your permission. Is it okay if we record this and then edit it and put it on the YouTube, on my YouTube channel?
Yeah, just send me a link.
Okay, all right, then.
Can we get a copy of the slides?
Yeah, I think so. I don't see any problem.
So you're gonna put up the
QR
QR
codes?
codes later?
Yeah, we'll put those.
Okay. All right, good.
They'll come right
We
after
get
this.
the slides and different things from them as well here.
We'll get the slides.
All right, but now we get a treat. Watch this.
So this I'll preface it this time, because last time I was at the Embedded World Conference 15 years ago. And we're sitting at the bar with my team, and the RTC, there's a couple of women there from the RTC magazine, Real Time Computing. They're with us too. We're just chatting. And then a song came on the radio, and I'm like, hey, we should go to karaoke. And I started singing this song. And right as I started singing the song, these two RTC gals stood up and they walked out of the room. And my colleague was like, nice going, Steve. You drove the women away. That's Monday. Do the conference, because that was before the conference started. Do the conference Thursday night. Turns out that me and a work colleague and two of these RTC gals from that same night, we go out and we're sitting at a bar as everybody else had gone home, so we're waiting for planes. And one of the gals pulls out her phone, and she says, do that song again. And I said, what song? That song you did on Monday night, do that song again. And I said, that was made up on the spot. Oh man, that was excellent. I said, I tell you what, I can't do it right now, but what I'll do is I'll write it out, and then I recorded it at the time. So that's what you're going to hear. It's the song that I wrote for Embedded World 15 years ago. Just a little OS, living in an embedded world. From one to many cores are there. Each OS must learn to share. They might divide with AMP or recombine with SMP. Just in case of an exception, don't forget your task protection. You want to share your interrupts. Do it right so that you don't corrupt. Some will win, others lose as they go on and on and on and on. OS strangers, coexisting side by side, sharing hardware, vectors all the time. Seeing inside of the target, profiling is necessary. If you want to know what's going on, working hard to get it done, then turn it off when the battle is won. Power is the key to life, conserve it to survive. Some will win, others lose. Serving tasks the scheduler will choose, and the process never ends. It goes on and on and on and on. OS strangers, coexisting side by side, sharing hardware, vectors all the time. Just a little OS, living in an embedded world.
That was fun. In real-time programming, I used to put on games 100 and I had to fight with our patch administrator just to get 5K to jump in, do the computer, and get out. And
Yeah.
it was the battle. And
Oh yeah.
it's the fun part of real-time programming.
Yeah, it's for me, embedded has been it's been my career. Most of it has been in embedded software and real-time operating systems. So that's it. Now, next steps. This is QNX everywhere. This left icon here. This is recently released. It's a complete version of QNX for non-commercial use. So you can sign up. You go online with that QR code. You can get a copy of the OS. It's ported to the Raspberry Pi 4, soon to be Raspberry Pi 5, and you've got a disk image. You can program it in an SD card, plug it in, and it's up and running.
Oh, really?
Are you on open source? You just
That
give
one,
it
yes.
away.
It's not open source, so
Giving it away.
Non-commercial.
yeah, if you need,
Non-commercial.
Yeah.
Because I'm actually going to charge. How much you? Yeah, we'll check for sure.
All right.
You'd have to get a quote.
How do you do the quotes? I'm just curious.
it depends on which piece we're doing.
Sorry?
It depends on what piece you need source code for. We don't open up the whole thing. We don't open up the
All right.
But if you needed something that we already have sourced for that maybe we don't release normally, then
If you're running
We
a
talk
farm,
about
let's see, how much is that, is that what?
well, that's part of the kernel. It's what's running on the ARM core itself, that the process manager and the microkernel itself. We don't open source that.
Okay.
I would say ever a customer that had deep pockets that really wanted it, we'd probably find a way to do it for them.
No, I'm not talking open source, I'm talking about the commercial one. How do you? do
We
it?
still need to make money. in order
Right,
to
right,
buy.
exactly, so I'm curious, how the license?
We have name user development licenses.
Okay.
And then we also have run times.
I'd like to have further conversation.
Yeah, VJ, you and Rich need to get together.
Mhm.
Just give me a bar.
Where's,
You're making it.
where are you hosting
Uh-huh.
the
I'll give
images
you-
right now?
It's on GitLab here. Actually, I don't know. I haven't
I'm
gone to
looking
the
right
links
now, like,
themselves.
Yeah.
So you can get to that link from here, but that's directly to some of the support pieces there with GitLab.
Hunting it down. Excellent. I've got some spare pipe words.
This is a next set. I know it looks like the same slide, but this one is free training. We offer, our normal course is about a week for just the operating system. And we took the first 4 hours of it and we release it free. So if you're interested in knowing more about QNX and the internals, you do this left one and you get a free training course. And there's a chance that I'll be doing the
Bill?
FAE session with it.
Bill, these are the second set of QR codes. So if you
Yeah,
want to
I
get a
got it.
picture of it,
I got it.
you got the first set. This is the second set.
Whoa.
Yeah.
2 sets.
I know, I was
4
surprised too.
there's actually 5 icons, but
Yeah, there's another one coming up.
we went overboard with icons, but I think these ones are really good because you can take advantage of them. There's also a white paper, precision in robotics.
Well, phone died, so I'm just checking what you're doing.
Yeah, you can send an email. That's fine. Okay,
So you already got.
You got 'em?
Yeah, I got it.
gotcha, okay.
Okay.
Trying to see if I can find it. You said Pi 4, that's like,
The Raspberry Pi 4 should be out there
I'm
and
looking
is
for it,
available.
yeah. I see the Docker images, but I'm looking for it. See if it's here.
All right. And then this is the last one, which is session feedback, and that tell us how we did. And so if you go on there,
Great.
Awesome, yeah.
oh, there you go. Tell my boss how I did. That's really what that's
All right,
about.
good. Hey, guys, let's give him a big hand.